Hello everybody. In this video, we're going to talk about double integrals in polar form, which is from 15.4 and 15.8. In the last video, we talked about Jacobian and its application to compute double integrals when we use substitution rules. So as an application of the Jacobian, we had following conclusion. So if we have xy plane, right? Xy Cartesian plane. And this can be converted to polar form, polar coordinate system, by substitution rule given by x equals r cosine theta and y equals r sine theta. So this is a kind of substitution from xy to r theta plane. And the Jacobian here is basically r, so it can be computed by evaluating the determinant of this, which is r. So eventually our main conclusion for this double integral is dx dy is equal to r dr d theta. So this is the conclusion of this formula. So dx dy is r dr d theta. Otherwise, all those things are the same. X can be replaced by r cosine theta, which is substitution rule, and y is directly replaced by r sine theta. So this is the formula we can use if sometimes the double integral is more convenient in polar coordinate system. And one common problem in double integral is finding an area of a given region. Then it is always like, so suppose there's some given region, then you want to collect all those coins with face value 1, which written as area equals r of 1 dx dy. But this is for xy coordinate. But sometimes if you want to try polar coordinates, then it's gonna be $1 value coins with this guy changed by r dr d theta. So this is actual computation of area in polar coordinate system. So the first example is finding the area for this butterfly shape lemniscate. And the equation of this curve is given by this. R squared equals 4 cosine 2 theta. And for the area, we don't, because of the symmetry of this butterfly, we only need to compute one part in first quadrant, the shaded part, and then multiply by 4 to get the total area. All right, so we focus on the shaded part. So the area is going to be R. R stands for the shaded area, and 1 r dr d theta, right? Now we need to know for those upper and lower limit of the running variable r, and upper and lower limit for theta variable. So when we do this kind of problem, so suppose we can think of following thing. Still, we're thinking of, so suppose, let me make it bigger. So suppose this is the area you are going to make double integral. And what you do is, for the area, you just put $1 value, right? Everywhere. $1 coins, and you collect. But originally, the Fubini's theorem tells us you can either go like horizontally, which is dx, and all the way to the from bottom to top, dx dy, or you can go vertically to collect everything from left to right, which is dy dx. But the polar coordinate system tells us you can actually go in a way that you're just sitting here. So this is your home, and you're shooting a ray or a light. So for example, let's say, right? And every time you collect all the coins lying, going through this light beam, and then you rotate this light beam from the lowest, which is starting angle, to the highest, which is the ending one. So this is the highest light beam you want to stop, and this is the starting theta you want to start with. So every time you want to find out the range of r first, so for dr, right, r is starting from 0. R is starting from 0, which is lower bound. And then R is ending at this point, which is, this point satisfies the equation of this curve. And the curve equation is given. So this point can be solved from this equation, which is R plus is square root of 4 cosine 2 theta. And for theta range, theta minus, which means where you start from this bottom light beam, which is 0 angle, and you're stopping at this light beam. If you look at here, it's a pi over 4, 45 degrees. So eventually we can rewrite this as from 0 to pi over 4, and 0 to square root of 4, I can take the 4 out from square root, then it becomes 2, and cosine 2 theta, and r dr d theta. This is the area for this problem in polar coordinate system. So we calculate the area and come up with this formulation, and the antiderivative is 1/2 r squared, and from 0 to 2 cosine 2 theta d theta. And if you plug in and calculate, then it is twice of cosine 2 theta d theta. And then the antiderivative of this is sine 2 theta, which is 0 to pi. Oh, sorry, it's not 0 to pi, pi over 4, and this is pi over 4. Then this becomes 1. And this is the part in the first quadrant, so you need to multiply total area is 1 times 4, which is 4. All right, next example. Before next example, we can conclude or summarize what we've done for polar coordinate computation. So first, sketch the region and label the bounding curves, and then find the r limits of integration, so r plus and r minus. So you think of, so suppose the region you're talking about is something like this, right? And this is coordinate system. Then what you do is you're pretending to shoot a beam at certain angle theta. Then what you do is you want to find where does this beam enter into the region, which is r minus, and upper limit is where it comes out from the region. Of course, this depends on which theta you're fixed with. This is for arbitrary theta, and then we can look at where theta starts from. So this is the angle which is theta starts with, and this is the angle where theta ending with. So first find r limits and then find theta limits. All right, let's see the next example. For another example, this is evaluating double integrals. It's not area, so it's the integral is given by this, and x squared plus y squared reminds us a polar coordinate system may be easier because we have x equals r cosine theta, y equals r sine theta, right? And then x squared plus y squared is 1. So it's not 1, it's r squared. So if you have something like this kind of term, then probably polar coordinate system will be easier choice. Also, one thing I want to do, I want to use a dx dy or dy dx is going to be the same as r dr d theta. All right, with this in mind, we can write the problem as e to the r squared, because this formula replace this, and dy dx is r dr d theta. Now I want to know those limit for r and for theta. Then we want to see what kind of region, domain we have. R is a semicircular region bounded by x-axis and curve y equals square root of 1 minus x squared. So it is basically semicircle, upper half of circle. So suppose the radius 1, then you can draw a circle from here. This is the equation of y equals square root of 1 minus x squared and bounded by x-axis. So we look at this yellow part, which means if I shoot a beam in any direction, then it's at the beginning, it's already in the region, so r is 0. R minus is 0, and r plus equals, so this is the ending part. So r stands for the distance from the point to the origin. So because the radius is 1, so everywhere, so r plus is 1, no matter how you rotate the beam. And for the theta, theta minus is 0 because you're starting from x positive half of x-axis, and theta plus is we're ending here, so this is pi. So now it becomes 0 to pi and 0 to 1 and e r squared r dr d theta, and antiderivative of this is e r squared 1/2 and 0 1 d theta, which means if I put upper limit, then 1/2 e to the 1th power minus e to the 0th power d theta, and this is just constant, so at the end we have this as the answer. Or you can write 2 as a whole denominator and e minus 1. One more example. So find the volume of the solid, like here, bounded above by the paraboloid z equals 9 minus x squared minus y squared, and below by the unit circle in the xy plane. So for the volume, if you have tangent like this, then it's just integral of that one. So the volume is that double integral of unit circle, the region, unit circle. So the domain we're talking about is unit circle in x and y. And z is the tangent height, and dx dy. So this is the volume formula for double integral. And because here 9 minus x squared plus y squared, this gives us the chance to try polar coordinate, which may be simpler or simplify the computation. So this is basically r stands for this unit circle, and 9 minus x squared plus y squared is r squared, and dx dy is r dr d theta. Now it's time to get upper and lower limit, but for this unit circle, this is easiest problem for region, or simplest region for polar coordinate, because whenever you shoot a beam, no matter which angle, it's starting from 0 and ending at 1. Oh, not 1. So the unit circle, yes. The unit circle, yes. So 0 to 1, yes. And then theta is in other words, the beam starts from 0 degree to all the way coming up to 2 pi. So we can write 0 to 2 pi. And then we calculate. So this antiderivative is 9r means antiderivative. R cube, its antiderivative is r to the 4th power divided by 4, and 0, 1, and d theta. And that gives us 0 to pi 18 minus 1, 17 d theta. So 17 over 4 times 2 pi, which gives me 17 over 2 pi. Alright, so we learned in this section, we learned how to compute double integrals using polar coordinate system. And it actually simplifies the computing for a class of problem, but it doesn't mean it always like that. So it depends on what kind of problem we have, what kind of domain we have, and try to choose one to the other way, whichever gives simplification of the computation. All right, we are going to stop here.